In this video, we will explore natural language processing technique called Word2Vec and try implementing it through coding. First, let's take a look at an example sentence. Suppose we have the sentence, "I will have food for dinner." If we want to insert a word between have and food, which word among Korean, sky, and computer would be the most appropriate? Certainly, the word Korean seems to be the most fitting. The reason is that when we examine the context around the blank space, we see the word have, which implies eating, and the word food, indicating something edible. Therefore, we might think of a word related to food, and Korean fits the context. A linguist once mentioned, "You shall know a word by the company it keeps," meaning that by looking at the words surrounding a particular word, we can understand its meaning. By observing the words around it, we can get an idea of which words are suitable and which are not. In other words, the meaning of a word in a sentence is not independent. It is understood through the words that accompany it. This is the most crucial point of Word2Vec, a natural language processing technique. In natural language processing, text encoding is a process that transforms text into numerical vectors, which a computer can understand. Word2Vec is one of the text encoding methods commonly used in natural language processing. And mentioned earlier, Word2Vec is designed to capture semantic relationships and context of words. Through this method, words can be represented in a spatial coordinate system, allowing us to infer similarity based on distance and direction. So, words with similar meanings or usage have vectors that are close to each other in this coordinate. For example, in the sentences, "A brown dog sleeps" and "a white cat jumps," corresponding words are brown and white representing colors, dog and cat representing subjects, and jump and sleep representing actions. Using Word2Vec, we can observe that similar words are positioned closely to each other in the vector space. In this way, Word2Vec enables the quantification of contextual meaning through vector representations, providing a way to capture the semantic relationships between words in a given context. As explained earlier, the key idea behind the Word2Vec method is the ability to determine which words are suitable or unsuitable based on surrounding words. In other words, words that fit into a blank space, as determined by the surrounding words, are considered to have similar contexts. To achieve this, Word2Vec employs two main architectures: skipgram and continuous bag of words, CBOW. The CBOW method predicts the target word based on the surrounding words. As mentioned in the previous example, predicting the target word between "I will have" and "food for dinner" is an application of the CBOW method. On the other hand, the skipgram method predicts surrounding words based on the target word. Using the example of the target word Korean, the skipgram method would predict the surrounding words in the context. Now, let's take a closer look at the continuous bag of words, CBOW method. The CBOW method takes surrounding words as input and predicts the middle words. Let's consider the example sentence, "The food industry grows in the world." In the CBOW method, to predict the word industry, the surrounding words such as the, food, grows, and in are used as input words. The word to be predicted, in this case, industry, is referred to as the center word, while the words used for prediction are called context words. To determine how many surrounding words to consider on either side when predicting the center word, a window size is defined. For instance, if the window size is 2 and the center word to be predicted is industry, then the two words before, the, food, and the two words after, grows, in, are used as input. Therefore, if the window size is denoted as n, the number of surrounding words considered for predicting the center word is 2n. Once the window size is set, the window is moved along, changing the selection of surrounding and center words. This iterative learning process, where the window slides and the model adapts, is known as the sliding window. Now let's delve a bit more into the skipgram method. While the continuous bag of words, CBOW method, predicts the center word based on surrounding words, skipgram does the opposite. It takes the target word as input and predicts the surrounding words, context words, within a specified window around the target word. Using the example sentence mentioned earlier with a window size of 2, starting from the word industry, it would predict words like the, food, grows, and in. While the continuous bag of words method is known to be suitable for scenarios with limited training data, the skipgram method is believed to perform well when there's an abundance of training data. Both continuous bag of words and skipgram utilize one hot encoding to represent input and output words as vectors, following a neural network training approach. However, detailed discussions on the training methods involve concepts related to artificial neural networks, and for brevity, we'll omit those details here. Now, let's try implementing the Word2Vec method in code. The Jupyter Notebook file is available on GitHub, so you can download it and run it directly. Typically, the Genzim library is commonly used for implementing Word2Vec. First, we'll store 5 sentences, from "this is good food" to "that is the worst food" in the variable documents. Next, we'll create a function to remove unnecessary stop words, commonly used words that don't carry much meaning in text analysis, and execute it. This will result in the removal of words like is and the. Afterward, by using the split command, we can separate each sentence into individual words based on spaces. Afterwards, we input the pre-processed text into Word2Vec to represent it in vector form. The min-count command indicates the minimum frequency for a word to be considered, allowing us to exclude less frequent words. The SG parameter distinguishes between skipgram 1 and continuous bag of words 0. Next, using the similarity command, we can calculate the similarity between two words, such as excellent and good, obtaining a value of -0.144. Additionally, the most similar command enables us to retrieve words most similar to bad in descending order of similarity. In the previous example, we used 5 simple sentences. Now, let's try using the movie review database provided by the NLTK library. To do this, let's first download the movie review database. Upon loading the movie review library, we can observe that it is labeled as positive and negative, with 1,000 positive reviews and 1,000 negative reviews. The dataset comprises approximately 65,000 sentences and about 1.58 million words. If we examine one of the positive reviews, we can see that it is composed of phrases like this. Furthermore, when we load each sentence, we can see that they are in the form of lists of words. We then input this text into Word2Vec, training it with a minimum frequency of 5 occurrences and using skipgram. SG is equal to 1. After training, if we calculate the similarity between actor and actress, we get a value of approximately 0.79. The similarity between actress and he is around 0.33, while the similarity between actress and she is about 0.5. Therefore, we can conclude that she is more similar to actress, indicating a connection to the feminine gender. Using the most similar command to find words most similar to mother in descending order of similarity, we can observe words like father and husband at the top of the list. Here, Vector 2 represents the model trained on movie reviews, while Vector 1 represents the model trained on the previous 5 sentences. When calculating the similarity between excellent and good, we find that Vector 2, which was constructed with a much larger amount of text data from movie reviews, shows a higher degree of similarity. Similarly, when listing words similar to bad using the most similar command, we see words like good, awful, and terrible, indicating much higher similarity compared to what was obtained from the model trained on the earlier 5 sentences.